Hi there, welcome back to the breadboard, and we have another review for you. This time it is the PIRL Charger. Yes, that's P-I-R-L, but it's pronounced Pearl, like the little thing you find in the oysters. I was sent one of these for review. It's, from my understanding, it's any moment about to go onto Kickstarter as a campaign. And what we have here is a 4-port USB charger. It is not a power supply and it is not a hub. It is a charger. It's designed for charging 4 simultaneous devices and providing up to 2.7 amps per port simultaneously. Each port is independent and they can tolerate short circuits, overcurrent being drawn and things like that without affecting the other ports. We'll do a little bit of testing with that when we go on the bench and have a look. The device also, as you can see here, has a numerical display on the top. This actually shows you the power being delivered to the ports, and it's updated several times a second so that you can see what power you are putting into your devices. Now, one of the things about the ports is that they're nominally 5 volts, but as you start increasing the current being drawn from the port, the controller inside here will actually increase the voltage slightly up to 5.2 volts before it then will flatline and try and maintain those volts coming out of the charger up until you get to about 2.7 amps. And as we'll see in our bench testing, around about 2.8 amps, it will actually shut the port down due to the overload condition, which is nice because it's going to protect your charger and it's going to protect your device. I want to point out that the unit I have is actually a prototype. It is not the production ready, hence the reason for the company going to Kickstarter to raise money for creating, I guess, the final aluminum moldings and things like that. So as we go through and we have a look, I will highlight some of the things that are more about the prototyping of it than what you would find in the production unit. This device was sent to me for free, and they included a 15 volt 4 amp power supply, and my understanding is that this power supply from Meanwell will also be included with the backers on Kickstarter. So that will be good news for the backers because that's quite a valuable additional item. Anyway, let's get to the website and have a look at the specs. Okay, here we are on the PIRL Charger website. It's www.pirlcharger.com, and right now it's geared for people signing up to be notified when this device is going to become available on Kickstarter. Now, I'm not sure what price this is going to be when it does come out on Kickstarter. I haven't had any indication of that from PIRL Charger Company. So just keep an eye out on the site. If you're interested in this device, just sign up on the site with your email and you get notified, and you will get notified as soon as any information becomes available. Right now we are 27th of May, so it's only a matter of potentially days before this is going to be on Kickstarter, and you can start putting in your bids and trying to reserve one for yourself. So let's go down and see what information is provided on the website. 4-port fast charging, 2.7 amps per port. We talked about that already. 10.8 amps in total. 4 separate channels. Now these are independent channels. They're not isolated channels as some people I think have indicated on other reviews. They're independent, but they're not isolated. So any disruption on one won't affect the other ones, simultaneously providing all 4 ports with up to maximum power for charging. It's intelligent device detection. So some mobile phones and things like that, when you first plug them in, they will probably start charging at, say, an amp or just under an amp, and then after some negotiation might bump that up to maybe 2 amps or maybe more or maybe a little bit less. This device, the PIRL Charger, will handle that communications and the protocols required to go between the normal charge and fast charging. Built-in watt meter, so when you first plug it in, when you're drawing very little, it will show you the watts with a decimal place after it. So 1.95 1.9 watts or something like that. When it gets up to 19.9 watts, as soon as you go over that, it then starts reading just pure watts, no fraction of a watt. Has a wide input voltage range. As you'll see when we have a look inside here, it's using a switching regulator on the input of this from your power being fed in to bring down the voltages to the nominal 5 volts required for the output ports. So you can feed it anywhere between 7 and 17 volts. It will quite happily consume that and enable you to charge your devices. It doesn't have a mains power supply built in, which is why I'm saying it is not a power supply. It is simply the charger. You need to provide your own power supply if you don't buy one during the Kickstarter campaign, where they'll provide one to you. But anything between 7 and 17 volts will work, and as long as it can provide the equivalent power. So if it's 7 volts and you need 50 watts, then you're going to have close to 8 amp power supply or something. If you're going to be up at the 17 volt range with your power adapter, then you can be way less. And the ones that they provided to me was a 15 volt 4 amp, but it's all about what power it can deliver, not what the actual voltage is, because it's using switching technology inside to convert it very efficiently to what is needed for the USB output ports. Consequently, it'll take a wide range of devices as far as sources for its power. You can use batteries, lead acid, lithium ion batteries, wall warts. You can use solar panels. It's really, plug it into your car, whatever you like. It's quite happy to consume all of those. It does have input protection for reverse connections up to the 17-18 volts as well. So just in case you do plug it in incorrectly, then you've got a good chance of it not doing any damage to your charger or to your connected devices. Built to last, it's got overcurrent, short circuit protection, ESD, reverse polarity, thermal overload. It is mechanically very robust, and as you'll see, it is very solid unit. I'm not going to try it, but it looks almost like you could probably drive a car over it without an issue. It's got a thick aluminum anodized cover on the front and the rear, and it uses FR4 material with the top and bottom layer being the anodized aluminum for dissipating heat and giving it a lot of rigidity. Real-world devices have been tested, so they've gone through a lot of different devices, testing compatibility with Apple, Samsung, Asus. The list is here, you can read it for yourself. 4 separate channels, we already mentioned that. It has a DC to DC converter built in to bring it down to the voltages required for each of the channels, and then there is electronic control circuitry for each independent channel so that they can run without affecting each other. So even if you're driving maximum current on one and minimal on another one, and then you go and short out the third one and overload slightly the fourth one, the first 2 are not going to get affected. In fact, none of the other ones are going to get affected, and we'll actually demonstrate that on the bench in a minute. Wire compensation, I already mentioned that. As you start increasing the draw on the output port, it will increase the voltage within a certain range, so that it will try to compensate for bad wiring. If you're using a slightly thinner USB cable, for instance. Fault isolation, we've already talked about that. Will handle up to 50 watts of power. So if you think about it, 4 ports, 2.7 amps per port gets you 10.8 amps. At 5 volts, that's going to be just over 50 watts of power. This is the maximum rating though, and it will get very hot, especially on the underside, if you run it for extended periods of time at the maximum rating. But typically people are going to be charging up their cell phones, their tablets, and various other things. Or in my case, I'm probably going to be using this for running a number of Raspberry Pi 3 Model Bs or B Pluses with LCD displays and things like that. So I need the ability to provide in excess of 2.5 amps at startup and spuriously, but in general it's going to be running and consuming a lot less power than that. The PIRL Charger can handle it. The chips that are built into the device are selected to be able to handle the high temperatures, but like any electronics, if you do run them at elevated temperatures for periods of time, you can run the risk of shortening the life of the device, but it shouldn't really be an issue here. Certainly the temperature is not going to kill it. It's got thermal protection built in and things like that, so it's just going to, worst case, shut down if it gets too hot. Best case, it's just going to get hot and it's going to be maybe toasty to the touch, but it's going to keep on charging your devices and things. So just be aware of that if you're using this and you're putting it on some kind of surface maybe that might mar with the heat that is being generated. You can't drop 15 volts down to 5 volts at 10 odd amps, so 50 watts of power, without generating some heat. We talked about the different input options. So coming down, built to last. Here's a little exploded view of the board. You can see here we've got the top and bottom, sorry, bottom's not there. It's anodized aluminum panels with FR4 boards in between, and then one of these obviously is being the circuit board. We will take our mine apart and have a look at it. We've talked about reverse polarity, we've talked about short circuits, we've talked about overheating and static discharge. It's got all the protections built in, so this thing should last you quite a long time. Here's just a few different views. Here's a view of the watt meter that is built into the panel. There's a little button next to it that you can press repeatedly and it will cycle through 3 intensities, getting brighter each time, and off. So if you don't want it turned on while you're using it, you can just cycle it through to the off position, or you can set it to a intensity that is comfortable for your viewing. Has 4 LEDs on the front panel. These indicate whether the port is being used and also the status of the port. Is it overloaded, short-circuited, etc. Now I did note during operation that the light actually doesn't come on until you're actually consuming over a certain threshold. I think it was about 300 milliamps of current from the port. So just because the light isn't on, it doesn't mean that you're not drawing current out of one of the ports. It just means that you're not exceeding a certain threshold where the light would come on and say, hey, I'm charging now. So specifications in a nutshell: input voltage range 7 to 17, current per port 2.7 amps, total current 10.8, output voltage 5.05. It will go up to 5.2 volts on each port as you start increasing the load. That sort of maxes out around about a few hundred milliamps. We'll check that when we're on the bench, and we'll just test it and make sure. The watt meter resolution 0.1 watt up to the 10 watts. Once you're over that, it goes to 1 watt. Accuracy about 5%. Now really, it's just giving you an indication that you're drawing a lot of load. It's not meant for a accurate test instrument to tell you exactly how much power you're consuming. If you want to do that, then there are way better ways of doing it. This is just giving you a crude indication of the amount of power that you're drawing, and it's the sum of all of the ports, not one individual port. Only weighs a measly 4.5 ounces, 128 grams. Output protection over current, dead shorts, recovers within 3 seconds once the fault has gone away. We can test that as well. I think there's a bit of hysteresis built in too, so you don't have to disconnect the fault or the faulty device. You just have to make sure the fault goes away. Even if, say, you go up to, say, 3 amps or more and it shuts down on you, as long as you bring it back down to, within the range, and we can test that too on the bench, see where it comes back, it should kick back in again. EST protection up to 18 kV, reverse polarity protection on the input up to minus 18 volts. So, if you're plugging it into a car or something like that, Maybe some vehicles might have a positive chassis on the vehicle instead of a negative chassis, who knows. Input ESD protection, thermal shutdown, all ICs equipped with independent thermal protection. So a bunch of reviews by other people that have already been done. I'm sure once I've done mine and posted it, mine might appear here as well. And if you want some information, you can email PIRLcharger.com, or as we saw at the top of the page, you can click up here, put in your email and click on notify me. They'll tell you when the Kickstarter campaign begins and how much you'll be expected to pay to get your hands on one of these, and there may be a few other options provided as well. I have no idea what the Kickstarter campaign is going to look like. So that's all of the specifications and what the website is providing us in a nutshell. So let's get to the bench. I have a few things set up, plugged into the already. So what I have is 1, 2, and there's one just off view here, 3 Raspberry Pis connected. One of them has a power meter in series with it, and it has an LCD display. This one here is a Raspberry Pi 3B Plus. I also have a DC load where I can adjust the load current. You can see here I've actually got it sitting, warming the device up with a constant 2.7 amps of charge, and you can see it's still measured at the end of these cables, giving us 5.01 volts, which is pretty impressive. Now, I did make up a special USB cable with 8 gauge or 12 gauge, might be 12 gauge wire, so it is extremely thick wire, so I minimize the losses in the wiring. What I'm interested in is measuring the voltage as close to the port as possible. So on this one, the 4th port, that's where I have this connector plugged into. All the rest of them are connected to Raspberry Pis, which typically draw an amp or more during normal operation. These two probably a little bit less. The one with the LCD display probably a little bit more. Anyway, let's go over the bench and have a look. Okay, here is our bench setup. We have the PIRL charger right here. We have a Raspberry Pi 3B, not a B+, with a official Raspberry Pi LCD display attached. We've got another Raspberry Pi. This one is a B+, 3B+, that is. And we have a 3rd Raspberry Pi here sitting inside this container running some Node-RED code on here. The 4th port here I have connected to my DC load, and as you can see, I'm currently drawing 2.7 amps, and I've got exactly 5 volts showing on the output, which is great for USB. I have, as you can see, a heavy gauge cable running from the USB port to minimize any voltage drops that may be experienced because of the cable. And the device is doing very, very well. So I have about 300 milliamps being drawn from Raspberry Pi 3B+. I'm not sure how much current this is drawing, but what I can do is flip the devices around to get a better indication. So I'm just going to power these off. A little bit naughty the way I'm doing this, but hey. Just pull that one. Oh, that was the wrong one. Pull that one out. There we go. Plug it in through the charging port, and this would be the B+, 3B+, that is. That's plugged in, a little bit of an angle, and this would be the other Raspberry Pi 3 in here starting up now. So I've lost a little bit of voltage because of this monitor. As you can see, it brought up the flag just for a moment as it was powering up on the display here. It's running there, it's back up again. So that's because we're losing a bit in this through it. It's reading 5.24 volts and 800 milliamps, so about an amp, probably spiking up to about an amp or more. I've been running the PIRL charger now with this load for a few hours, and it's warm to the touch, but it's not excessively warm. In fact, if I bring up my thermal imager on my FLIR DM284 multimeter, we can see here is the PIRL. Where right here. So I'm just going to hold it up so that we can get a square on view against it. And what we're reading is about 38 degrees. Let me just bring it in closer. There's a spot temperature reading on this. So it's about 38.7. It's interesting that the writing, because it is white, it's actually reflecting differently and showing up on the thermal imager, which is kind of interesting. We're drawing about 20 watts according to the display on the PIRL. And if I just turn it over so we can meter the temperature on the back of the unit, which typically gets a little hotter. That's sitting, and it's been sitting right directly against the bench here because I don't have any rubber feet or anything on the bottom of this, and it's reading about 45 degrees. So that's not terribly hot. The loads that I have on here are, I would say, fairly typical of a normal use. All right, I'm drawing a heavy load over here as if I'm charging something. The Raspberry Pi 3 with the LCD display, that would be equivalent to charging a tablet or something like that. We've got the Raspberry Pi 3B Plus running. It's just running the standard GUI and things, nothing special. And we've got another one running industrial applications. And we're still only drawing about 20 watts, so that's about half of the power that this thing could deliver. So what I'm going to do is I'm just going to plug my phone in. It's not sure how charged it is. It's 14%. Actually, it's giving me low battery warnings. So I want to plug that in and let's see what it will do as far as the power is concerned. I'm going to leave the first channel, the fourth channel, running my 2.7 amp load. Oh, actually, before I do that, what I want to do is short out the load on this channel, just to verify that the Raspberry Pi and everything else does not have any issues, like it doesn't crash or anything like that. Just going to find something to poke in there to short it out with. We should get a fault indication on the PIRL LED to indicate that there's something weird going on. So let's stick a pair of pliers in here and short it out. Alright, that's now indicating 0, and you can see on the display now we're down to 8.5, 8.3 watts on the PIRL, and you can see there that we now have a red indicator light come up to indicate there's a problem. Now, at the same time as all of that, we still have no issues with the Raspberry Pi running Octoprint. It's stayed there, it hasn't crashed out or anything like that. So that shows that the channel is running completely independent of the other three channels and has not affected them when I shorted it out. So now I'm going to take this away and we'll see how quickly that gets back up to current. 2, 3. So it's not recovering, probably because it's still trying to draw 2.7 amps. And I've basically, because I shorted it out, it's tripped it over there. I think what it's doing is the controller is probably sampling every now and again to see if the load has reduced. So let's see if we can crank this down a little bit and see where it may come back on and actually start providing a current again. There, came back on. So 2.3, 2.29, so say 2.3 amps. Let's just try, set that at 2.3 amps. So let's try that shorting out. So it's 5.05 volts, 2.3 amps. Let's short that out. Now let's see how quickly it will recover. As quick as I pulled my pliers out of the socket. So that's pretty good. It took the volts right down, took the current right down, didn't affect the other ports. So the next thing to do is I'm going to slowly reduce the current. And what I want to do, I'm just going to zoom in more on the PIRL here so that we can see it. So you can see here that the light for channel 4 is on, channel 1 and channel 2 is on. Channel 3, the light is not on, probably because this Raspberry Pi in the industrial case is just not drawing enough current to make a difference. So remember I said to you that when we were running, in the video, that this current had to be low enough to sorry, the current had to be high enough in order for that LED to come on. It doesn't go on just because you're drawing, you know, a few microamps or anything. So I'm going to crank down the current being drawn on my DC load until that light goes off. And I think it's around we're down to 500 milliamps, 300 milliamps. There, it's off. Let's just slowly creep it up until it comes on again. There, 300, just as soon as I go over 300 milliamps. I don't know how quickly it'll go off again. Looks like it has a little bit of hysteresis, so it's probably not flickering. So it comes on at 300, goes off. I'm down to 200, just over 220. So 300 milliamps, it comes on. I'm sitting at about 300, well 294, close enough to 300. So that's showing there that, you know, if you're using it as a charger, which is what its primary function is, then usually once something's finished charging, it's going to be drawing very little current. The light's going to go off. Give you a rough idea that it's finished charging and it's probably in a trickle charge mode. If it's on overload, the light's going to go red, you know, like short circuit or overload. If I take it actually on overload, let's just go way back up again. As soon as I go over on the amps and it shuts out. There. See, the light's gone red. So it indicates that you have a fault condition. You bring it back down, it goes back to white again. Now the other thing that I was going to show you here while we're here is the display. It's a little tough to see with the lighting, but you can press this button and cycle through, so it's off, dim, bit brighter, full brightness. It's actually reading 12. There we go. If I change the angle a little bit, it's easier to see. Now increase the watts. See, it's slowly going up there to give you a good indication. So it's quite readable. It's a little harder to pick it up. I've gone overloaded it. Bring it back down again. There we go. So I guess that's the operation of it. There's not really much else operationally to show. I mean, I could go through and do the same test on each of the other channels, but from my understanding they're all identical, so it really wouldn't make much difference. What I will do is I'll put my phone on, and I'm going to use this indicator to see if we can see it bounce between, there we go, closer view, normal mode and fast charge mode. I don't know if my Samsung Galaxy S5 will do fast charge, but we will see. I think it does. So there it's plugged in. Actually it's gone straight to it actually went straight above to 1.5 amps and then back down to 1.14. Let's just leave it there for a moment, see if anything changes. I'm not sure if this particular phone, oh there you go, jumped up to 1.6 amps. So yes, it does negotiate, and it will handle giving it more power if it's needed. So there you go. I don't think there's really much else to say about it or anything except to take it apart. Let's have a look inside. Okay, from what I can see, there's the full cover case. You can see the thick aluminum panel on the top and on the bottom. There's the main PCB, and we have several FR4 PCBs which are used to make up the sides of the case. Just screwed right through into the bottom panel. So let's take the cover off and have a look inside. Okay, 4 screws. Let's lift the lid off and have a look inside. There we go. So first thing to note, let me just set these down. So this is the lid, as you can see, the button, display, 4 more LED ports, and what we have is we've got the multi-layers of PCB FR4 material that's been stacked up, and we have what looks like a 3D printed part here. Now I've already been speaking to the guys at PIRL, and they tell me that This is 3D printed for the prototypes, but they're looking at doing injection molded parts for the production run. They're using light pipes just with little LED dots to bring it up to the 7-segment display on the top, which is a nice little neat and easy idea to implement. 4 separate little light pipes, for one for each channel here. So now looking at the main PCB here, what we have here, this is our main DC jack input. So I see no magnetics up here in this area. So what we're going to have probably is a power supply protection, input protection circuitry. It's going to be very, very close to this connector. We're going to have a regulator somewhere in here, which is going to be providing either a 5 volt or 3 volt 3 for this controller, which is over here. Looks like we have an ISP programming port over here. Here's the 7-segment display. You can see they're just surface mount white LEDs just on here, and they shine up through the light pipe to give you the display. And then what we have are 4 identical, except for that one diode up here, basically 4 identical channels, one for each output port with its own magnetics, which means it allows it to control its own voltage and provide some level of independence from each of the channels. So when one draws more and it needs a slightly higher voltage because of the current being drawn, the other ones don't have to go up with it, which was what happens in some of the other devices that you may see in the market. Okay, so one more layer I've just gently prized off. There's a piece of conductive heatsink tape on the back of the PCB so that we get the magnetics and everything via this side. You see a lot of vias to stitch through for heatsink to basically wick the heat from the magnetics and the chips here through to the bottom of the board so that it can go onto this and onto the aluminum underneath. So that just sits on there. So I'm just going to get a magnifying glass and have a little closer look at the PCB so we can see if I can identify some of these components. Okay, so a couple of unexpected things, nicely unexpected, but unexpected nevertheless. I was expecting to see one input buck boost regulator or something like that up here, but there isn't one. What we have is we've got some input protection, and we've got a shunt resistor here, which is probably being used to measure the overall current being drawn by the system, and there's probably some voltage measurements going into this chip up here, which is an AT-Tiny microcontroller from Atmel. What we have for each of the channels is we have a buck regulator for each channel independently, and we have a USB charge controller with line compensations, which is what's going to be upping the voltage slightly as you start to increase the load to compensate for any losses that you might see in the wiring going out to the device being charged. So we have this duplicated for every single channel. What is also surprising is that the LEDs for indicating the status are 2 independent LEDs, one white one to indicate that it's charging, and a second separate red one to indicate that we have a fault condition. Outside of that, there are no bodge wires on here. Based on how perfectly aligned all of the resistors and everything else are, I would say that, or guess, that this is probably one of the first ones from actual automated assembly, and it's probably just been hand assembled to send it to me. So the board is very, very clean. On the back of it, there are no bodges or anything like that. Again, very, very clean. So overall, I would say that the build quality is very, very good. All of these devices, I will provide a link to the part numbers in the description so that you can have a look and you don't have to take yours apart to see what's in it. They've all got built-in thermal protection, ESD protection, the USB charge controllers that connect directly via a couple of small value resistors to the ports. They're the ones that are providing the ESD protection and everything else to each of the ports independently. So the whole thing is put together very, very nicely using a very good selection of parts. For instance, the USB charge controller is from Texas Instruments. The microcontroller is an Atmel AT-Tiny, as I said, now microchip. So yeah, good choice of parts all round. So I guess the only thing left now is to put this back in the box and make sure I haven't broken anything, and wrap up the video. So anyway, this is the PIRL charger, about to go on Kickstarter any day now. The end of May we're at, so it's touted to be launched beginning of June. It's a USB charger, not a power supply. You have to provide a separate power supply to run this. It can be from a wall wart, can be from a car battery, could be from a solar panel, could be from lithium-ion batteries. Anything between 17 down to 7 volts are sufficient to provide it. Now obviously the higher the voltage, because of the buck technology being used here, then the lower the current that your wall wart would have to be. I do want to just mention that, you know, this is a really, what appears to be a really nice design, nice and clean, very straightforward, and I wish them all the luck with their campaign. As I said, I do not know how much this is going to be, but I do look forward to seeing it made available and to see what kind of price they're going to charge for it. Anyway, that's it. If you liked the video, give me a thumbs up. If you don't, well then don't. But I hope to see you on the next one soon. And if I have any more information provided to me, I will put it in the comments for the video as well. For instance, when the Kickstarter campaign kicks off, I'll put a link to it so you can go and have a look yourself. You can preempt that by going to their own site and signing up yourself directly with the PIRL Technologies on the PIRLcharger.com website. And if you really like it, then you can buy one for yourself. As I said, this one is sent to me officially as a prototype so that I can have a look at it, provide some feedback to you guys, and that's it. So see you in the next video. Bye.